We're going to take a look at example 20.5. The problem here is to find the output current and the current gain. Of course, that's AC current, and we're going to first of all do that by rearranging the circuit as an AC equivalent model. To do that, we remember that we short circuit all the capacitors. We short circuit this resistor, of course. This resistor disappears from the circuit completely. And we also bring all the DC voltages to zero. So this 10 volt supply VCC then really gets connected here to the return, the ground. And so RC becomes in parallel with RL, R1 becomes in parallel with R2. So the circuit looks something like this. Where here is R1 parallel with R2. And then this comes into the transistor, which the emitter goes directly to ground because the resistor RE is completely bypassed. The collector sees two resistors. One is the resistor in the collector, RC, and the last one is the load resistor, RL. Now there's one other element in this, and that is, of course, the resistance inherent inside the transistor itself, Re prime. So now, the first thing we want to do is we want to find the input impedance. The input impedance of the circuit, Zin here, to the circuit, is equal to the parallel combination of R1, R2, and this emitter resistance in the base, Z base. Now the easiest way to do this, to add up parallel resistance, to combine the parallel resistance, of course, is to do it as conductances. And so what we're going to do is just simply say that Zin to the circuit is equal to R1 in parallel with R2 in parallel with Z in the base. And we can rearrange this so that the calculation becomes a lot easier. 1 over Zin equals 1 over R1 plus 1 over R2 plus 1 over Z base. Now we know what R1 is, it's 18K. We know what R2 is, it's 4.7K. What we don't know yet is what Z base is. Well, we should remember, hopefully, that Z base depends upon these two characteristics of beta and Re. So Z base is equal to beta times Re prime. And in this case, we're given Re prime, so we don't have to calculate the collector, the emitter current to find it. And that is equal to beta is given to us as 200. The emitter resistor Re prime is given to us as 25 ohms, and so Zin at the base is equal to 5,000. So we can put all these numbers into this equation over here. 1 over 18K plus 1 over 4.7K plus 1 over 5K. And that comes out to 468 millimoles. And therefore, we can just simply flip this over. Zin is equal to 2.14 K ohms. So that's probably the simplest way to calculate the input impedance of the circuit. Next, what we need to do is we need to find the output impedance as far as the collector is concerned. That's to say the AC collector impedance. That is designated R, little r, C. And that's equal to RC in parallel with RL. And that, of course, is 1.5K times 5K over 1.5K plus 5K. And when we turn the handle, this turns out to be about 1.15 K ohms. From this point, what we can do is simply apply an equation which has been provided for us that gives us the current gain. Now, we've already showed you how to derive this expression, but rather than going through the derivation again, we're just simply going to make use of it. The current gain is equal to HFE, that's the AC beta, times Zin times the emitter AC resistance RC, Z in the base, times RL, the load resistance. So we know all these numbers. This is simply equal to 200. The beta, or the HFE, was given to us as 200, times Zin. We've already calculated what that is. It's 2.14K. It's right here. RC, we've already calculated here, 1.15K. And then we have Zin to the base. The Zin base is 5K. And RL, which is 5K. And again, we just churn the crank, and we get a current gain of 19.68. Since we know the input current was given to us, IN, is equal to 500 microamps, we can therefore find out what the output current is. I out is simply I in times the current gain. And that is simply 500 microamps times 19.68, and that equals 9.85 milliamps. And that's the AC current that's flowing in the load resistor.